Now, how are we going to find this line of best fit, so to speak? We're going to call this the regression line, or oftentimes they will abbreviate it as LSRL, least squares regression line. And right now, we're going to look at how to find the regression line by using technology. Our calculator is going to do all of the work for us to find this regression line. The equation of the regression line is y hat equals b sub 0 plus b sub 1 times x. Really think about it as y equals mx plus b. That's all it is. All it is the straight line that we're used to dealing with ever since we started algebra. Y equals mx plus b, where m is slope and b is the y-intercept. However, you'll notice in this formula, they write it as y hat equals b sub 0 plus b sub 1 x. So they have flip-flopped the slope and intercept from the form that we're used to. So b sub 0 is the y-intercept. And b sub 1 is our slope. So it's the same thing as y equals mx plus b. It's just written in a different form. And the other thing that looks weird is, why does this little y guy have a hat on? Okay, y hat is how we pronounce it. So we say y hat equals b sub 0 plus b sub 1 times x, where the hat is supposed to signify that, hey, I am a prediction for y. This is a prediction line. And that's our ultimate goal in this unit. If you remember to the first slide, is we're trying to use x to predict the value of y. So the hat is just reminding the reader or whoever's looking at our work, saying, hey, I have a line that's going to help me predict what's going to happen in the future, or what's going to help me predict what should have happened yesterday. Okay? So this regression line is, again, just a regular line, y equals mx plus b, but the notation is different. Okay? So really, m is b sub 1 and b is b sub 0. So the y-intercept comes first, plus the slope times the x value. Now we're going to use this example here to see how we would use the calculator to come up with this line. So what they've done here is they've looked at a Ford F-150 pickup, and how many miles does the pickup have on it, or the truck, and then what was the price sold. So if I know that I have a F-150 with 200,000 miles, can I predict how much money I would get when I go to resell it? That's what we're trying to do with this problem here. So I know the amount of miles on the vehicle. Can I use that to predict the sell price? So you can see they randomly went to an Auto Trader magazine and they picked out different Ford F-150s with different amounts of miles and how much the truck was sold for. So let's take a look at how we would come up with this line on our calculator. So everybody should have a TI graphing calculator now. So let's grab this guy and bring him over here and take a look. So what we need to do is, like we spoke about in Unit 2, our lists are going to be our best friends. The more that we can get comfortable using the lists, the easier our life is going to be. So again, we find our lists in stat, edit, or there is a list function, which would be second stat, which is list. I prefer to use stat, and then I just hit enter for edit, and it brings up my list. So I've gone through here and put in every single value in my two lists. Now remember, any regression problem is explanatory response relationship. And in this problem, we're trying to see if we're trying to use the explanatory variable as the number of miles and the response variable as the price. So explanatory, response. Explanatory, how many miles does a truck have? What's responding to the number of miles would be the price that we would be able to get for the truck. So again, we type all of the data into our lists. Explanatory is always list 1. Response is always list 2. Explanatory is L1. X comes before Y. A, B, C, D, E, F, G, X, Y, Z. X is always first. So we put X in L1. We put Y in L2. Okay. Now I'm going to have the calculator do all the work for me to find the least squares regression line. So in order to do this, I need to tell the calculator what it is that I want to do. So now after the data has been entered, again, X in L1, Y in L2, let's look at the steps to find the regression line. So on the right of the calculator, you will see the key steps, the key press history of how to do this. Okay. At first, it might be a little bit confusing and quite a few steps, but we'll do it enough so that after a while, it won't seem difficult at all. Okay. I want to find the least square regression line. Okay. In order to do this, I need to go to Stat, Calc. So I toggle over one, and then it says lin reg A plus BX. It's the linear regression equation in the form A plus BX. The calculator doesn't have a subscript, so it uses A as B sub 0 and B as B sub 1. Be careful that we do not use 4. We want to use lin reg 8 or A plus BX. And then the calculator is going to ask us, okay, where did we put the X data? Remember, X is always in L1. X comes before Y, L1 comes before L2. So I tell the calculator my X list, all my X data is in L1. All my Y data is in L2. Again, it's asking us about frequency lists. Never ever mess with the frequency list. Leave it alone. Okay. Just leave it blank and you'll be happy. So I put my X in L1. Yep, I put my Y in L2. Do not mess with frequency list. And then it's going to ask me, do you want me to store the regression equation? Yeah, that'd be nice. The calculator will keep the equation in its brain for us, and we can go back and look at it later on if needed. So let's put it in Y1. So to do that, we're going to go to vars or variables, toggle over to Y variables, function, and then we'll see a Y1. So we're telling the calculator, please do all the work for linear regression, where we put our X data in list 1, we put our Y data in list 2, and we would like you to keep that or store that equation for us in Y1. And then we'll just tell it to calculate. And check it out, Y equals A plus BX. So you can see here that this equation, A is 38,257.13507 and B is negative 0.1629. And if you look at the equation in the book here, it's the same thing we had. Y hat equals 38,257 minus 0.1629x. Okay. So the calculator just came up with this equation of this blue line right here for us. Okay. Pretty cool. But it didn't give us R, the correlation. How strong is this relationship? Remember, R is going to tell us direction and strength. The calculator didn't do that for us, but it can. First, we have to tell the calculator what to do. We need to turn what's called the diagnostics on. In order to turn diagnostics on, we would go to the catalog. So if you go to second 0, which is catalog, and now we're going to go to diagnostics. I'm going to hit this green D. You notice that our calculator has different colors. So the green, if we're in alpha, which as soon as we go to catalog, the calculator automatically switches to the alpha command, which means if we hit a button, it's going to be what shows up in green. So I'm going to go to D because I want to find my diagnostics. And then I'm going to go down until I can find diagnostics on. Keep going. I went too far. Slow down. Stop. Okay. Let me go back to diagnostics on. And I'm going to turn my diagnostics on, and it should say diagnostics on. You hit enter one more time and it says done. Cool. Now it will give me R. But unfortunately, I didn't have my diagnostics on when I did the work the first time. That's all right. We'll do it again. I'm going to clear the key history so we can see the process of finding the linear regression. So we go to stat, calc, 8, lin reg a plus bx. We put all the x data in list 1 and the y data in list 2. Again, we leave the frequency list blank, and we're going to tell it where to store this equation once again. So I wanted to put this equation in y1 for us. So to find y1, we go to variables, y variables, function, y1. And then we tell the calculator, okay, do the work. Now we get R and R squared. Now R is negative 0.81. Should not be a surprise, because if we look at the slope of the line, it's negative. Clearly, the association on this line down here is negative. It's going down from left to right. The R value or correlation will always have the same sign as the slope, or the B sub 1. So R and slope will always have the same sign. We can tell if R is positive or negative just based off of the sign of the slope. And then we see this other value here, R squared. Okay? R squared, we're going to talk about here in a minute. It also, all that R squared is R times R. So they took negative 0.81 times negative 0.81 to get this R squared value of 0.6642. Okay. Now again, all this equation is trying to give us a prediction line. So if we know how many miles are on our truck, we know we can predict the price that we would be able to sell it for. This calculator steps might be a little daunting at first, and don't worry about it. It's not a big deal. Don't get too hung up on the calculator. Worry about what it is that we're trying to do. We're trying to use the X. If we know the X value, can we use that to predict the Y value? And in our example here, we're trying to use the number of miles on our truck to predict the price that we could sell that truck for. So there was a lot here in this section, a lot of calculator stuff, a lot. And I just closed my calculator instead of moving it. All right, so again, we're trying to find this equation y hat. Why is there a hat? Because it's prediction. Okay, slope and intercept just like normal. Okay. So let's see if we can make a prediction. Okay. My truck has 300,000 miles on it. So if I have a truck with 300,000 miles, can I use that to predict the number of, can I use that to predict the price? All I'm going to do is 300,000 miles. That's my X value, because you can see down bottom here that X is the miles driven. So if I want to predict for 300,000 miles, I take this number 300,000 and I plug it in here for X to this equation. Okay. I don't want to do that by hand though. I want to use my calculator to plug that in. So let me find my calculator again. So I want to know for 300,000 miles, I want to take that 300,000 and plug it into the equation. The calculator's pretty slick in the way that it will do it for us. Remember that in our Y equals, we have the equation. Y equals 38,257 minus 0.162 X. It's already in there for us. So I could take 300,000 and do all of the work. So I could, if I wanted to, go in here and do all of the math, but that's too much work. So instead, I'm going to ask the calculator to do all the work for me. Remember, we're the brains, the calculator's the muscle. The calculator is going to do all of the heavy lifting for us. So I want the calculator to plug in 300,000 into Y1. So I tell it Y1, plug in 300,000. And it's going to do the work for me. It's going to take that 300,000, it's going to plug it into the equation, and it's going to make a prediction. So it did negative $10,618. Okay. So it took the calculator took this 300,000, plugged it in for X, did all the work for us, and spit out an answer. Pretty slick. So we got Y hat, when we plugged in 300,000, we got negative $10,618. Let's think about what this says for a minute. Okay. It says that if my truck has 300,000 miles on it, I can sell it for negative $10,618. Wait a minute. I'm going to have to pay somebody $10,618 to take my truck from me? That doesn't make any sense at all. Nothing was done wrong here. All the math was correct. That's what our model tells us. Our model tells us if your truck's got 300,000 miles on it, you're going to be able to sell it for negative $10,000 approximately. Makes no sense. This is an example of extrapolation. Extrapolation is when we use the regression line to predict too far beyond the scope of the data used for the model. In this model, we only had trucks up to about 150,000 miles. So our least square regression line, our Y hat, our prediction line, will do a fairly accurate job predicting, but only within the scope of the data that we have. If we try to predict too far beyond the scope of the data, it's called extrapolation. And oftentimes we're going to get nonsensical answers. It's not going to make any sense at all. We know that we would never pay somebody $10,000 to buy our truck. Okay. So extrapolation is when we use the regression line to predict outside the value of outside the X values used to come up with the model. Okay. If you think about humans, well, we grow at an incredible rate as babies. So we could come up with a model for how fast a baby would grow, but we couldn't use that model to see how tall a 60-year-old person would be, because using that model, a 60-year-old person would be 500 feet tall. We know that doesn't make any sense because at some point we're going to quit growing. Well, same thing with the price of a truck. At some point, once the truck reaches a value of $0, well, obviously, we're not going to be paying a bunch of money for somebody to buy our truck from us. So be careful when you make predictions. Okay? Always go back and ask yourself, does this make sense? Okay? So easy to make predictions. I would like to know how much, what would be the prediction if my truck had, let's say, 80,000 miles. So again, to make this prediction, you take 80,000 X and you plug it in. Okay. Or you could use the line now that we have this line on the graph, 80,000. We go up here and across 80,000 miles. We predict that we get about $26,000, $27,000 for our truck. And we could find that value by plugging 80,000 into the equation. All right, so we've seen how to make a scatter, or we've seen how to construct the regression line, but we haven't seen how to make a graph on our calculator. So if we come back to our original data set, let's graph this line. Let's make a scatter plot. So we talked before about scatter plots, and it's kind of laborious to make one by hand. We have to draw the X and Y axis. We have to scale the axes. We have to put the values on the axes. We have to make sure we label them. And then we have to go in and painstakingly plot each and every data point. Well, you know what? The calculator does all the work for us. So let's take a look. If we go to stat plot, which is second y equals, we go into our stat plot. I'm going to turn it on. And I wanted to make a scatter plot, which is the first one. It's already highlighted. Again, the calculator is going to say, okay, cool, I'll make this for you, but where's my data? X is always in list 1, Y is in list 2. Now we're simply going to tell it graph. Uh-oh, I don't see anything. That's okay. That's going to happen almost every time in stats. But remember, we have a cool function in here to help us. It's called zoom stat. So you go zoom 9, and it's going to automatically fit this in for us. Okay? And since we already did the work for y equals, or we already did the work for y hat and we put it in y1, it also graphs the line. So the calculator just did all of this for us. And you can tell that these two graphs are the same. The calculator found the least square regression line, or the line of best fit, which is just trying to minimize these vertical distances the points are from the line. So make a scatter plot, simply go into stat plot, turn it on, it's already on, and then make sure we highlight scatter plot, which is the first plot. And then we just hit graph, zoom 9, and will give us all the dots. And we've already seen how to get the equation for y hat, or the prediction line. Again, if we try to predict too far beyond the scope of the data, we might make fools of ourselves, okay? Extrapolation, really it's called extrapolation, but you could think about it as extrapolation, meaning I was trying to predict extra, way too far out. Be very careful in doing that. Oftentimes you'll make yourself look like a fool. Okay, so extrapolation, predicting too far beyond the scope. Any sort of prediction we want to make, just plug X in and do the work. All right. So now that we've looked at how to make a regression line, how to make a scatter plot, what R and R squared, or what R is, how we find the slope and y-intercept. So this 38,257, that value would come if we plugged 0 in for X. So if you could think about, if we drove 0 miles, we could sell our truck for $38,257. So in other words, it's telling us that's the starting value of the truck, or that's the price of a new truck. That's really what the slope is. Or I'm sorry, that's really what the y-intercept is. The y-intercept is telling us what is the starting value. When X is 0, what does Y equal? And the slope is telling us the rate of change. We'll get more into that here in a moment. All right. We're looking at the same data set here. Okay, here's our regression line. Y hat equals 38,257. We have all of the data points, and we have our least square regression line. Now, remember that we need to talk form, direction, strength. Form, direction, strength. R, or the correlation, gives us both direction and strength. Okay, where does the form come from? And that's what we're going to be working towards right now, is how to determine, is this data linear or not? Basically, that's the form, linear or not linear. We're going to use residuals to determine if the data is linear or not. A residual is the difference between Y and Y hat. Okay, so residual is Y minus Y hat. Another way to think about a residual is observed minus predicted. OP, O minus P, or Y minus Y hat, or the actual Y minus the predicted Y. Observed, how much did we sell that truck for? Predicted, what does our prediction line or our regression line predict we would sell it for? The difference between those two is what's called the residuals. And they've been mapped out here for us on this graph. You can see at, for example, at 75,000, the truck actually sold for around $21,000. But our model predicted that it was going to sell around $27,000. Okay. So the residual is that leftover, that difference. The residual is the vertical distance from what we observe to what we predict, or what the actual value was to what the predicted value was. So a residual is just the difference between what our prediction line says is going to happen and what actually happened when we went out and gathered the data. An interesting fact about residuals is they help us make this line. This line is placed in such a way to minimize these vertical distances. Okay? It's called a least squares regression line because what it's doing is it's finding these vertical distances and it's making a square out of them. And it's placed in such a way that the sum of all these squares is as small as possible. Okay? Residuals, well, there will always be positive and negative values. The sum of the residuals, so if we took all of these values, positive, observed minus predicted, so all the ones above would have a positive residual, and all of the points below the prediction line would have a negative residual. If we were to add up all of the residuals, the sum would always equal 0. By definition, by the way that the least square regression line is calculated, it always is placed in such a spot that the sum of the residuals is always going to equal 0. Every single regression line in the world will have that same property. The sum of the residuals will always equal 0.